Hello everyone. So in the previous video, right, this is more specifically to we were learning how to back propagate from scratch. So we learned how we usually back propagate. So that was the part one of the video. As the next part of the video, right, we will see how we can create this neural net and then back propagate and tweak these data and everything so that our model is learning and we are getting better results as we go ahead. So we'll see that. Okay. That means we will be creating this neural net specifically from scratch, and then we'll see how backpropagation helps the neural network to learn. Okay. So before just jumping onto that, right? So, if you have seen in neural nets, right, one thing I will just take the piece of code so that I don't need to type it out. So, this is the piece of code for the time being. Just remove, or we can comment this up. Okay. So in the neural networks, means this is very just I am taking one of the new. Sorry. So I am just taking this as a neuron, okay? The unit building block in a neural networks. And if you see right here, usually these are the inputs that come. There is a weight associated with each of them, and then we add a bias term as well to this. So usually the equation looks somewhat like this. So these are the inputs. These are the weights that we are assigning. This is the bias term, and the equation looks like this. So x1 into W1 plus x2 into W2 plus bias. So this is how the equation looks like, okay? For a single neuron, okay? But there is one more thing that is known as an activation function. So again, this is something which is pretty interesting in terms of you calculate all of this, but after that, right, we implement something known as an activation function. And there are different types of activation functions. One is a non-linear activation function. So the intention, or I can pause this video and you can go through this one. So the intention is to capture if there is any non-linear pattern in the data. Okay, because all of the equations that you see here, right, are linear equations, and obviously they are also trying to capture some pattern in the data at the end of the day. That's the intention, is that based on the input, right, and the output, the training data, we try to understand is there a pattern in the data. But these are all linear equations that you see, right, and they help us capture some way a linear relationship between the input and the output. So we introduce a activation function to capture specifically if there are any non-linear patterns as well in the data. Okay, so just go through this video of Andrew and Jenny. He explains it pretty well in terms of why we need this activation function and what is non-linear activation function and why it is required. So one of the non-linear activation function is tan h. Okay, so tan h is one of the activation function. If you see the graph, right, so tan h is this one. So what it does is, right, whatever value we get out of we get out of this, right? X1 into X2 plus X2 into W2 plus B, right? That value can range from anyone minus infinity to positive infinity, right? So when we implement tan h, this blue line, it squashes that data in between minus 1 to 1. And means the main intention is that it puts the data in that specific bucket so that it's not flowing in the minus infinity range or in the positive infinity range, and to give us a bit more of a control in terms of how the neural network behaves as well. So let's go ahead and do that. Okay, so this is the one, and this is the tan h and everything that we are going to implement. So okay, so we as of now haven't defined tan h, so let's go ahead and define that. Just to make sure I don't do any errors. Okay, so if you saw the tan h equation here, right? So it's e to the power 2x, whatever x we pass on, right? E to the power 2x minus 1 by e to the power 2x plus 1. So whichever node is calling this, right, we take the data of it, and that is equal to dot exp 2 into x you can just store it somewhere, so x equal to, okay, and x minus 1 divided by ex plus 1. That's the equation. Equal value tan h value will put itself is there, and so the output we are getting, right, it has single child as the self. Now next is we have to define backward also for that, how we were defining here, right? So just going through this here, right, if we see the differentiation of tan h, right, it's usually 1 minus tan square h itself. Okay, so while defining the backward, right, so 1 minus tan square h, and as we were doing in the previous as well, right, multiplying it with out dot grad, and out dot underscore backward is equal to backward. Sorry. Written out as well. Okay, so that's the backward e to the power 2x 1 is 1 by to the power 2x plus 1 tan h, and backward is 1 minus tan square h into plus equal to, yeah. So that's it. Sorry. So it will be n. Okay, and if I do a draw dot of, alright. So this is what we are getting, x1 into w1, x2 into w2, they're both multiplying, we are getting here, and then we are adding that up. This is what we are getting, that is the bias term. We add that, we get an n, and we apply a tan h, and obviously this is 0, and if I want to calculate the tan square h, right, it is coming up fine or not. Oh, sorry. Tan h whole square. So this is the tan h value that we are getting, right? 0.9910. Okay, so this is what you see. So that's it. So we calculate the tan h here. That is 0.9910. Okay, we can remove this. We don't need it anyway. So this is 0.9910 that we got here as tan h value, and to calculate the gradient of this, right, we need to do 1 minus tan square h, and that is 1 minus 0.99, so 0.0179, 0.0179 that you are getting, that is here. And then obviously it's a plus, it's getting percolated, it's again a plus, it's again getting percolated the same value, and here because it's multiplication, we multiply this by gradient of this to get this, something like that. So that's what we'll get here. So that's specifically a neuron that you can say in a neural networks, and that's what we get. The same, right? This implementation that we are going, right, it's goes into the same line as how PyTorch we see the implementation. So let's see how we can implement the same thing in Torch as well. So by the time it loads here, right, in PyTorch, this is how we explain. So x1 is again um, torch we'll say, and we put that as a double value. And we have to explicitly specify that we want to calculate the gradient for that variable or not. Okay. So like that, and more so, right, usually in Torch or something, right, we directly pass arrays, 2D arrays, 1D array or something like that. Usually we don't work with single value, so that's why you are saying that I am passing it as an array rather than a value or something like that, because that's what it is made for. So we define all of these, we specify that we want gradient of that, then we are calculating, this is the bias term, we are calculating this equation, then we are doing the tan h and we are getting the output. Let's see what value we get here. So the tan h that got calculated, right, the value is similar, 0.9910. X1 grad is 0.0537, that's what you see. So it's both of them are similar. So we just saw, and basically this is the library that we will be using later. Obviously we won't be using the microgrid. It's just to give an explanation or from scratch, right? If to see how this is implemented, and this specifically goes with how torch or the spy torch, right, internally that's how it is working, and that's what the intention to show that. Now let's try to build our neural network here. Okay, so one thing, if you see here, right, that's what I was specifying, that one of the neuron means in whole of this, right, one of the neuron is this, where we take the inputs, we take the weights, we add the biases, do the activation and get it here, right? Okay, so first we'll define our neuron class. So few things that you saw for a neuron, right, is that will be the number of these inputs that we are feeding into it, means the number of these inputs that are going to come, and the same will be the number of weights as well. Okay, so that's what I need. I need the number of inputs that will be coming into this neural networks. So we'll initialize two things. Initially, anyway, the input is what we will be giving this, but these weights and the biases, right, they will be random to start with. So for these many inputs, right, I sorry. So here I'm taking random values for all the weights in in uniform way, means -1 to 1. It will be a uniform distribution that we'll taking, and uh, I don't remember why it has specifically needs to be a uniform distribution. I can look up and let you know, but I think we can randomly take values as well. I think it will just take more time to converge the neural network or something like that. That might be the reason, but I can um, I can look up to in terms of why it is supposed to be uniform distribution. Again, so that's the bias term. Now let's define when this will be called, right, with the input. This again, just remember this specifically. So this x that is coming, right, x will be this, and So first we need to take each value of x, each value of w, multiply it, and then add the bias term to that. Okay. So this will be for weight and input in, usually use the zip function. So weight x. Okay, so we are getting two of these values there, and what we are doing here is multiplying both of them. That's one thing is done. So this multiplication part we have achieved, and we need to sum them up as well. Sum, right? Sorry. Okay, so what this will do is this will generate these things as x1 w1, x2 w2, x3 w3, like that it will generate. Okay, and then it will sum all of these. So sum these as well plus the bias term as well. This is the actual value that we are getting. Once we get that, we need to do the tan h of this. Okay. That will be the output of this. Okay. So if I have to define a neuron, let's say this neuron itself, we are defining where we have two input terms. Okay. The same thing we are trying to define here. Okay. And in we calculate with an array of, what is the input? 2 comma 0. So the data that you are getting is, right, is this data that you are getting. So why that is different is because the weights here we are taking as random and bias. So if we take these term itself, right, we'll get that value itself. So that is the neuron is what we have defined. Now let's define a layer. Okay, and then we'll plug all of the layers at once. So each layer, right? So each layer, if you see, one thing is the number of layers, right, is one variable which the user need to specify how many layers they want. Second is how many these inputs are coming into this, means the information about the previous layer, how many numbers of layers are there. So if you take something example like this, right, this has say 3 and here it is 4. So how many inputs, such means 3 layers, and for each of the neurons, right, we have how many inputs? 1 input, 2 inputs, 3 input, 4 inputs, and this depends on how many neurons we have in the previous layer. Okay, so here um, so one is, this is the number of inputs that are going to come into the layer. Some I have taken it num because that's what we were somewhat specifying it here, how many inputs that are going to come, and in out you can just think of it in terms of the number of neurons in a single layer. Okay, And so we will create, sorry, range n out those many neurons. Okay, so just, and for each neuron these many inputs that are going to come. Okay, right. So for the number of neurons, just create this variable. So the layer will store an array of these neurons. Okay, and here when this is called, right, again this will be called with x itself. So what we need to return is, for each of the neurons, right, we need to do that calculation. I will need to return, uh, yeah, let's first do the calculation itself. So previous diagram where it went, whatever is this, yeah, this is the one, right? Okay, and we are putting the activation here itself. It can be a different layer also, and so we can define one more layer just for the activation, but here we are doing the activation as part of this itself. So all this equation plus it. So this is what we are getting it here. Okay, so for n in self dot layer, we'll go through each of them, and n will call x. Okay, so say we get input, um so we get input like this via weights. So we multiply all of them, do the activation, and then return an output. Okay, that's the intention here. Fine. Now we have defined layer. Now we need to plug all of these together. Okay, right? So we need to plug this layer, giving the input to this layer giving the input to this layer, and this layer giving how many number of layers and everything, right? So this is what is known as multi-layer perceptron. And so here what we are taking is, here num is a bit different in terms of the number of layers the neural net has, and in each layer how many number of neurons we have. Okay, so what we are doing here is, okay, anyway, let me do that. Here we are storing the information for each layer. And each layer wants the number of, so what is happening here is, Okay, there. So the thing is, it takes two inputs. One is the number of input layers, and later a array of each of the layer and how many neurons in there. So something like this. So you can, if we have to initialize MLP, right? Something where it is. Different. So, here, okay. So what that MLP is, right? It will be something like this. Three. Okay. What is the intention here? That two number of inputs. So if we say we are making this one, right? So it will be three number of inputs going, and then 4 4 2. Okay, 4 4. So anyway, it returns the class of that, whereas for each, right, and then we can specify the inputs as well. So MLP, we can we need to define that anyway. So let's define how the calculations will flow through these. Okay, the input that we are getting. So for layers in each of these layers, right? So it should be something like this. Now what is happening is, um, we are taking these inputs, okay? All of these weights and everything are initialized, okay? So initially, and all of these layers have also been defined previously, okay? So we are throwing in our input to the first layer, okay? That is this part, okay? So we are calling this layer with all the inputs, okay? With all the inputs, and then what is happening it with all the inputs, right? Each of these neurons are getting called. So input remains the same, whereas for because the same thing goes in here, right? So if you see where it went, if we have any value for that, oh, let's take this one, okay? This is again a single neuron. Something like this. So this x1 remains the same for each of the, just take this as a neurons itself, right? So this x1 is going here, x1 is going here, x1 is going here, and it is multiplied with the value that is associated with that. So that's what is happening here. So it takes the x, it calls the layer, it means I'm not getting a good picture. Let's go with this itself. So it is calling this with all of these inputs, okay? All of these inputs, it is calling this layer. It calculates all of them, and each of them, right, returns the value that is getting calculated here, which is in this, okay? So for each of the neuron here, right, it is taking the weights, the inputs, calculating the sum, adding the bias, doing an activation, and that's what this guy is returning. In this way, for each of these, right, we are returning 1, 2, 3. So we'll have three values coming out of it. Okay, so this list that you see here, right, will be throwing us all of those values. So let's do this. So Let's keep it simple. So we have three inputs. Let's take two, just a simple one. Okay. So this means we are taking three inputs, okay, and we have two more layer. Here we have two neurons and one neuron here, okay, and three are the inputs. So and MLP we can call three inputs, right? So 5 comma 6 comma 7. You know, oh sorry. Let's initialize this. Okay, it is not initialized, I think. Yeah. Defined. Sorry, it's supposed to be N, right? We should be seeing only one data. I'm not sure why we are So the thing is, the last layer, right, is two here, one here, so we should see only one value. Okay, it's getting two, but when I give it as one, it still comes as two itself. I'm not sure why. We are just getting two values, is it? Why only two values we are getting in here? This is after each exit is getting okay. So three input, two and three, okay. Um, so first layer has two, then the next layer has three for n dot x, so it should have calculated three. Why am I getting two values here? And one more thing, it is just getting called once and out. So these are the two layers. Okay. One thing is it should be outside this loop because it will go ahead and then should be the final output. So I think now it should work. Yeah, now it works. So we can do it anyway. Three and finally sorry. So this is one value that you are getting out of it. The neural networks, okay? So three inputs are going in here. Three inputs are going in here. We have three here, and three and then one neuron only. These are not there. So three and then one. Okay. That is what you see here. So that is that, and then let's see how we can train the models as well. But one thing is important is anyway, let's do that. So let's take the input right because we are taking two. So let's take three examples. Like I can just copy paste it directly from here. Okay, so this is the input. For each input we should have three, so we have three variables for each of them. Okay, so these are one of the examples. I mean, first this will go as an input, then this will go as an input, this will go as an input, and then this will go as an input. And for each of those, right, this is what we are expecting: 1 minus 1 minus 1 and 0. Okay, so that's one thing. So let's do this. So for um input in XS, calling M with INP Okay. So this is the predictions that we got, and if you see, right, they are way far from. Just give me a minute. Just give me a minute. I could not see my screen. Yeah, it's up. So this is the prediction, and if you see, right, they are way off from what um we are expecting. So 0.4 it should be 1, 0.41 it should be minus 1, 0.43 it should be minus 1, 0.43 something 8222 this should be 1. So that's now we'll train our these neural networks, these neurons, the weights and everything, right? So that we reach closer to this value. From here is what we are getting. Okay. So now let's do that. So for say, oh no, we can do this as well, right? And then we'll calculate the loss as well. I missed to calculate the loss. So here is what we were doing it, right? At the end, we need to calculate the loss. So at the end, whatever value you are getting, right? If you want to increase it or decrease it, right? Based on that, you will calculate all the gradient, and then you will use those gradient to make sure the final output that you are getting, right, the z value should increase or decrease, right? So that's the same intention here. So we'll calculate say loss that will be equal to for y predicted and y actual. Okay, so these are the actual values, these are the predicted values. We'll do a zip we predict y as y predicted. We'll take this instance. Okay. Minus, anyway, we will be squaring it up, so it doesn't matter. Sorry, not this one. So we are taking each of these, means 0.40 we are taking one and seeing how far they are from their this thing. Sorry. It is y. haven't defined the power, is it? Okay. So the problem that we are seeing here is, right, once this output that we get, right, is of value type, okay, but the problem is we haven't defined the square root here. So we need to define the power as well for the value so that that gets calculated. So let's do that then. Def under underscore. So we are overloading this. So when the power gets calculated, right, this is the function that will get called. So we can just copy paste it for the time being just to save time here. So what's happening here is, first it will just check that the power that we are supporting, right, should be a int or a float. That is what it is. And simply we are doing the math operation of self.data into the square and returning it as a value. That's what we were missing when we throw that error. And we also need to define the backward for that. So backward for that, if you understand, right, differentiation. So what usually happens is here. So if x to the power n, n comes in front x and then the power of n minus 1. Okay. So what's happening here is, so this you can say is self dot data power of other. Okay, other is in the top. So other comes in the front into self dot data, again the power of other minus 1. So that's what other, this is other and this is self dot data. So other into self dot data power of other minus 1, and that other minus 1 is what you are getting. Okay. So this will get calculated here, and out dot grad you put it in there and then you call this up again. Okay. So now this should work. So this, oh sorry. This should be sum as well. So means we are just specifying the overall performance of this. So um, um, so this is the performance of our model as of now, and this is where 4.73 is, you can say we need to reduce this, we need to make it much more closer to 0. How it will get closer to 0? When these values that we are getting, right, get closer to these values, that's when that will be lost. So and one more thing we need to do. So anyway, let's do that. So for gain range, let's say we want to so two things. um I'm trying to just consolidate here. So we are making a prediction, which is the forward pass. We are making a prediction. We are calculating a loss. Okay. Then what we need to do, we need to call backward. Okay. That should be loss dot backward. Okay. But before that, if you remember, right, we had to initialize this with 1, and I think that was taken care here itself. I'm just forgetting. Yeah, so it was taken care itself here, and then the gradient was getting calculated. Okay, so loss dot backward, so it will do that, but then we need to, sorry, code is getting calculated here itself. But after that, we need to update these values as well, right? Means this data that you see, right, using this gradient. So what it is saying is, if you want to increase the value of O, do a positive change to it, means increase the value of N. Gradient positive value is telling that. In the same way, uh, there is any negative, so gradient here negative shows that decrease the value of x2, that will help you increase the value of O. Okay, either you maximize or you try to minimize or something like that. Okay, so the gradient value tells, oh, sorry, let me, so this is what we are trying to do here. So gradient, right, it tells us this is the gradient. Okay, so if it is positive, right, this is the equation. What we need to do is we need to decrease the value of W so that the value of O, so W you can take it as an N. Let's take it as an N. So N you are getting a positive value. This means N is somewhat here. This is the gradient value of that. So that equation is telling reduce the value of W, that is the negative of gradient. So N minus gradient, okay, that will help you move to this direction. Okay, so this is N, this is O. Okay, O is tan H of N. So N reduce the value, gradient opposite of gradient. So if you are getting a positive gradient, you need to reduce the value. If you are getting a negative gradient, which will be like this here, you need to increase the value. Okay, so opposite of the gradient that you are getting. But we need, so what, which all values we can tweak is these weights and biases, right? These are the parameters or the levers which we can tweak and get the value of that, right? So we need to store it somewhere. Then only we'll be able to tweak the value. So, def parameters self return. So what I will do, I will pick up all um, the errors and return it. So here anyway it will be self dot. I'm just returning. Okay, sorry. So it is returning a list of all the weights and the biases for that neuron. Here I am collecting the weights for the number of neurons in the layer. So for mm, so for parameter sorry. So in layer, right, has array of neurons. So for n in self dot layer, this means for each of the neuron in the layer. Then for parameters in and dot parameters, okay, so for each of the neurons in this layer, call these parameters, collect all of them and store it. Okay, so this is to just create a single list of all the neuron, all the parameters. Okay, so in one list we will have all the parameters. Why I am collecting that? Because we need to tweak those values. Okay, If you're not understanding anything, right, just let me know. And here we are going through again. Now for each layer, okay. So for L in self dot layers, for P in sorry, L dot parameters. So for each layer, call call this parameter column and then store it. Okay, so here we have collected all the parameters. So now we will do a update here. So for P in M is the object for that. Okay, M dot parameter. I'm getting all the parameters. M dot data plus equal to right. Sorry, not M dot data. P. So what is happening here is, so if I just take this example, I am telling it, say for this is one of the parameters whose value we want to tweak. So I am saying n dot data, okay, change it to 0.01 by how much amount. With this gradient what we are getting, right, 0.0179. Obviously, as I told, if gradient is positive, we need to reduce, so minus of the gradient. So that's what you see here, this minus value that you see here. So if the gradient is in this side, if it is negative, we need to increase the value of W. Okay, we need to move this side so that we are getting the minimum loss that we see here. Okay, this is the J-mean, the minimum loss. So we need to move here. So just to move here, right, if that is minus gradient, say minus 0, minus 5, so we need to minus of that, so that will be plus 5, so W plus 5, so it will increase the value for us. Okay, so that's where this negative signs come in, and by how much we want to do. So this is something which is tweakable. You can do it anything, means uh, because at times, right, gradient can be huge as well, small as well. So by how much? So if you specify this very high value, right, it might happen that you change it so much that it goes this side, because the value was so high, right, that it goes this side. Or if it is too small, right, it will take a lot of time to come, something like this, it will move. So you need to find somewhere in between value that helps you reach this loss. Okay, so um, so this is error. LPS no attribute parameters. Let's initialize that. Let's initialize this. Okay. So that's the error that we are getting. Okay. Let's run it once. Just capture this error. So the next time we should see a small loss. What happened? No, it increased, huh? Sorry. Okay, let's loop it around. So as I told it, if that, let's see why it's happening. So we got 4.85 increase, increase, then reduce, 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 then increase, repeat, reduce. So if I do it something like this, right? 9595. See, it is slowly converging, but it is coming down. Okay, so if I do it like a 200, see, it has come down here, but it is very slow actually. See, you are seeing this much 0.37. Now, if I ask for what is wipe red light, now see, 1, this is 0.86, minus 1, this is minus 0.73, minus 0.77. So that's much how much it is done. So if I train it again, right? So this has gone much more closer to 1, this has gone much more closer to 1, this has gone much more closer to minus 1, this has gone much more closer to minus 1. And that's where you see the loss has reduced a bit. So that's how basically neural network works in terms of you do a forward pass. uh, I mean, for each of the value you calculate it, you calculate the loss, then do a back propagation, and then you update all those values that you see here, right? So these datas are all can be tweaked. That's what we learned previously, right? What is the impact of this on this, the impact of this on this on this. These are all the gradients, those are storing. So it is telling if it is a positive, it is telling if you increase the value of W, O will increase. But here we took loss, right? We have to reduce the loss. So we need to do ulta. So, or opposite, we need to reduce the value of N to get this reduced. But this is positive. So that's where this negative sign comes in and by how much we want to. So this is again a tweakable parameter or something like this. You can make it very small as well. So something like this. Very slowly it will converge and everything. And if you do this right, again it is much more closer to the expected output. So we need to find that value. So that was in total what is backpropagation, and how neural networks usually backpropagate to um come nearer to this and everything. So now once we are seeing right, we have minimal loss, then we can give it any input, okay, and allow it to predict. So this thing, right? Um, Now if we see, if we try to see a pattern here itself, right? If the things are one right, if we see this is I'm just trying to form a example here. So if these two are negative, right, I see this is coming positive. So let me give some value in those range, okay? So if I want to make a prediction, right, let me take 2 5, hopefully that is -2 here. Let's see what predictions we get from this. Oh, sorry. So you are getting a positive value, and that's what we see, right? If we, I mean, it's kind of expected that it is going somewhat similar to this 2 5 a bit high value minus 2 somewhat like this. So expectation was we'll get near about 1, and that's what we are getting. It's near about 1. So then we can do the prediction for such values or something. So that's what or how neural network works, and that's backpropagation from sky. So thanks a lot. And if any one of you have any queries or anything like that, right, post it in the comment section. Thanks again. Bye.